We Group 9 are going to present the research paper, MANIKIN, Biomechanically Accurate Neural Inverse Kinematics for Human Motion Estimation. To start with the abstract, accurately estimating full body motion from sparse inputs such as head and hand poses is a critical challenge in mixed reality. Traditional inverse kinematic methods optimize joint angles directly, often leading to errors that propagate through the kinematic chain, resulting in misaligned end effectors or unrealistic poses like floating hands or ground penetrating feet. To address this, we represent MANIKIN, a biomechanically accurate neural IK solver that refines the SNPL model with anatomical constraint, reducing degrees of freedom to mirror real human motion. MANIKIN introduces swivel angle prediction to perfectly match input poses while avoiding implausible configurations. Through extensive experiments on motion capture data, we demonstrate state-of-the-art performance in both accuracy and realism, all while maintaining fast inference speed, enabling more immersive and responsive MR experiences. Next, the challenge of sparse input in mixed reality. Mixed reality systems rely heavily on sparse input, like head and hand poses, to estimate full body motion, a challenging task due to error accumulation in traditional kinematic chain. While data-driven approaches have improved accuracy, existing methods still struggle with misaligned end effectors, unnatural poses, and poor generalization. Optimization-based techniques are slow and prone to local minima, while pure learning methods often fail on unseen data. Additionally, standard models like SNPL allow unrealistic joint rotation, leading to implausible results like floating hands or ground penetration feet. To address these limitations, we introduce MANIKIN, a biomechanically accurate neural IK solver that combines swivel angle prediction with anatomical constraint for precise real-time full body tracking. MANIKIN reduces hand position error from 5 cm to 0.1 cm. It reduces the error from 5 cm to 0.1 cm, outperforms state-of-art methods in configuration, and a refined SNPL model that enforces biomechanical possibility. To address these issues, as we discussed, we propose MANIKIN, a novel neural inverse kinematic solver that combines biomechanical accuracy with real-time performance. Our key innovation includes three things: anatomically constrained SNPL refinement, reducing degree of freedom to mirror real human motion; swivel angle prediction, which analytically derives joint configuration from limb geometry, ensuring precise and effector alignment; a hybrid neuroanalytic pipeline that is differentiable for end-to-end training, yet fast for real-time inference. Now, the inverse kinematic for human motion, challenges and solution. Inverse kinematics has long been a cornerstone of human motion estimation, with applications spanning robotics and computer animation. However, traditional IK solver often produce unrealistic poses, while recent hybrid approaches combining deep learning with optimization remain slow and prone to local minima. Methods like hybrid IK demonstrate the potential of neural analytic integration but rely on full body cue points, limiting their utility for sparse effector tracking gap our work address. On the model-based front, SNPL has emerged as the standard for 3D pose estimation, yet its unconstrained 3 degree of freedom joint rotation often violate biomechanical plausibility. With prior works enforce realism through data-driven priors or transformers, they fail to guarantee anatomically valid joint configuration. For motion capture from sparse input, two dominant paradigms exist: IMU-based system and MR device tracking, example headsets and controller. Recent advances like avatar poses in Agrol leverage transformers and diffusion models to estimate full body poses from end effector data, but they either depend on post hoc inverse kinematic optimization, sacrificing real-time performance, or they lack biomechanical guarantees. Our method bridges these gaps by unifying neural network with analytic IK, ensuring both efficiency and anatomical fidelity, advancing the state of sparse input motion. MANIKIN introduces a biomechanically accurate neural IK solver that overcomes key limitation in sparse input full body tracking. By integrating swivel angle prediction with anatomically constrained SNPL refinements, our method achieves sub-centimeter end effector accuracy while avoiding implausible poses. Experiments show state-of-art performance in realism and speed, enabling precise motion estimator for AR/VR. This work bridges the gap between data-driven learning and biomechanical fidelity, setting a new standard for real-time human pose estimation.
Okay, so now let's talk about the proposed solution, which is MANIKIN. MANIKIN is designed to solve the problems of estimating the entire human body pose using only sparse inputs like head and hand positions and orientations. What makes Mannequin different is that it integrates these powerful ideas of biomechanical constraints and neural network. Biomechanical constraint basically refines the popular SMPL body model by reducing the unnecessary degree of freedoms, which means that the joint movements will stay realistic and physically possible. And the neural network predicts the torso joint angles, foot poses, global orientations, and the swivel angles for the arms and legs. So it's a basically combination of smart modeling of the human body and smart prediction using deep learning. Now we'll move on to the next slide, which is about torso forward kinematics and analytical inverse kinematics. So what torso forward kinematics do is it takes the predicted torso angles which are predicted by our neural network to compute the positions of the shoulders and hips, which are the base joints for the limbs. These positions then become input for analytical inverse kinematic solver. What this inverse kinematic solver do is it uses the predicted swivel angles and the known positions of the shoulders, hips, hands, and feet to analytically compute the joint angles for the arms and legs, such as elbows and knees. So this process gives us a closed form solution, meaning it's exact, fast, and most importantly, it guarantees physically realistic limb movement. Now moving on to next, which is the full body pose estimation. So why this mannequins approach is so important? Because in mixed reality we usually only have a few tracking points like the head and hands, but we still want the full body avatars, natural looking movements, and reliable alignment with the real world. So this creates a very challenging problem because many full body poses can produce the same hand and head positions. So that's what we call an ill posed problem, right? So mannequin solves this by ensuring the predicted poses are biomechanically possible and making sure that the end factors, the hands and the feet, are precisely aligned with the input and eliminating artifacts like feet sinking into the ground. In short, Mannequin provides the foundation for precise, real time, and realistic avatar control in AR and VR using only a few sensors.
Now, I'll explain how Mannequin uses swivel angles to model human limb configurations accurately. In biomechanics, each arm or leg has 7 degrees of freedom. But when we fix the shoulder and wrist positions, or the hip and ankle positions, we only constrain 6 of those degrees. That means there's still one free parameter left, and that's the swivel angle. The swivel angle also determines how much the mid-joint, like the elbow or knee, is rotated around the straight axis connecting the base and the end joints. In other words, even if the hand or foot position is fixed, the elbow or knee can still move along a circular arc. The swivel angle controls where exactly on that arc the joint should be placed. This gives us way to resolve the ambiguity of limb pose from sparse inputs. Now, to use swivel angles during training, Mannequin needs ground truth values, but these aren't provided in the existing dataset. So, the authors of this research paper compute them from joint positions. They form a triangle using base joint, mid joint, and end joint. From this, they calculate the center of elbow's circular path, the radius of the circle, and finally the swivel angle using vector projections and trigonometric identities. Now, instead of predicting the angle phi directly, which is discontinuous, they predict cosine and sine of phi. This way, the network avoids jumpy transitions near 0 and 2 pi, and the training becomes much more smoother. They apply two losses. one on the predicted cos phi and the sin phi, the swivel angle, and the second on the predicted position of the mid joint to make sure it lands on the correct arc. These two losses together ensure the network learns swivel angles that are both accurate and physically plausible. Next, once the swivel angle is known, MANIKIN uses analytic geometry to compute the full configuration of the limb without any iterative optimization. This is important because it guarantees speed, which is the solution when the solution is computed instantly. It ensures physical plausibility such that the joint angles follow biomechanical constraints. And it's fully differentiable, so it works seamlessly with neural training. The analytic solver works for both arms and leg by taking in the base position like the shoulder or the hip, the end effector position like the wrist or the ankle, and the predicted swivel angle. Using these, it calculates all the internal joints exactly through geometric formulas. Now, these are the steps of the analytic solver. The first step is the mid joint flexion. This is the elbow or the knee bending angle and is calculated using the law of cosines from the triangle formed by the limb bones. So the next step we have the base joint swing rotation. This moves the upper limb segment like the upper arm or thigh towards the direction of the motion. It aligns the base to mid vector correctly. Next, we have the base joint twist. This rotates the limb around the upper bone to match the end effector exactly. The twist is computed from the distance the hand or foot needs to travel along the elbow's arc. For arms only, there's step 4, which is the elbow twist. This controls the rotation of the forearm like when we turn our palm up or down. And finally, we have step 5, which is the wrist swing, which is calculated by subtracting the elbow twist from the wrist's global rotation. So these 5 steps give us all necessary joint angles for the limb in a way that's fast, exact, and anatomically correct. Now, we have end-to-end differentiable training. So, even though parts of the system use exact geometry like full MANIKIN model is training end-to-end, this is possible because all the operations, including the geometric ones, are differentiable. So the neural network can be optimized using gradient descent as usual. The final loss function includes several components, like a rotation loss on local joint orientations, a foot pose loss to keep the feet grounded, a torso FK loss to match upper body positions, and finally the swivel angle loss and the mid joint loss, all that we have discussed earlier. These combined losses guide the network to make precise, biomechanically valid predictions from just head and hand inputs. Now, SMPI-based datasets like AMAS are often containing joint positions that look fine, but when we extract the joint angles, they may be biomechanically impossible. So this method where MANIKIN uses swivel angles and geometric inverse kinetics to reconstruct full body poses with high accuracy and physical realism, all from sparse tracking data, can be used to refine SMPL datasets, making them more accurate and useful for applications like healthcare and rehabilitation, biomechanics research, and training motion-aware machine learning models.
In this section, the authors evaluate the performance of MANKIN. The key objective is to demonstrate how MANKIN improves over the SMPL based methods, particularly Avatar Poser, AG Roll, and Avatar JLM, in terms of motion accuracy, smoothness, and real time usability. For training and evaluation, three subsets of the AM ASS dataset, CMU, BML RUB, and MPI are used, alongside a real world VR motion capture dataset for sim to real testing. The evaluation employs standard matrices like MPJPE for position accuracy, MPJVE for velocity error, and regional errors such as HPE, UPE, and LPE. It also uses jitter, which quantifies the motion smoothness, and ground penetration evaluates the physical realism at the feet. Comparisons Yes. Comparisons are made against lightweight and heavyweight variants of baseline models. AG roll and avatar poser are adopted into casual variants using only past frames like Mankin. The Mankin variant includes Mankin S and Mankin L, which are single frame output, and Mankin LN, which is a sequence to sequence version, to enable the fair comparison with AG rule, which uses longer frame sequences. Results on AMS's dataset shows that the Mankin significantly outperforms Avatar JLM in both accuracy and speed, achieving up to 20 times faster inference with fewer parameters. In cross dataset evaluation, Mankin shows superior generalization across motion types, outperforming all baseline on every metric. Visual comparisons further highlight its ability to produce smooth, natural, and biomechanically possible motion. So we can see that Mankin's design anchored in biomechanics and neural inverse kinematics enables high accuracy real-time motion estimation with stronger generalization capabilities. This validates its potential to use in VR, animations, and embodied AI applications, etc.
Now we'll explore the ablation studies and mannequin generalization to other motion estimation tasks. So the key objective here is to evaluate how different inverse kinematics or IK method and swivel angle estimation approaches impact mannequin's performance, and basically how well it generates to estimating full body poses from sparse 3D input points, specifically from the head, wrist, and ankles. So we'll begin with table 4, which presents ablation results on the MPI dataset. So the metrics here include MP, JPE, and various pose estimation errors across body regions. Our full model achieves the best overall performance with the lowest MP-JPE of 6.41, indicating the most accurate joint predictions. We can observe that removing either the upper or lower body IK module significantly increases the error, which underlines the importance of holistic IK modeling. For example, removing the lower body IK increases MPJP from 6.41 to 7.06, and likewise substituting our approach with alternative IK strategies like optimization based or learning based IK leads to a noticeable performance drop, reinforcing the efficacy of Mannequin's design. So now moving on to table 5, we examine Mannequin's ability to generalize to another task, predicting full body poses from just the head, wrist, and ankles. This is a more challenging problem due to the high sparse input, yet Mannequin still outperform baseline across all tested model backbones. For instance, when paired with the transformer architecture, Mannequin reduces the MP-JP from 5.34 to 3.74 and the full body MP-JV from 22.74 to 14.98, a substantial improvement. Similar trends are observed with RNN and MLP backbones, further demonstrating Mannequin's versatility and robustness. So, to conclude, these results highlight two things. First, Mannequin's carefully designed IK pipeline and swivel angle estimation are critical to its accuracy. And second, its modular design allows to generalize effectively across different pose estimation tasks and neural architectures. Next, coming to this slide, this discusses one of the core limitations of the mannequin framework. It depends on prior knowledge of the subject's body dimensions, particularly accurate bone lengths within the skeletal model. So basically, mannequin assumes that it has access to precise anthropometric data for the subject. This information is crucial for producing reliable pose estimations because even small inaccuracies in bone lengths can lead to significant errors in joint positioning or orientation. So while this assumption holds in controlled environments such as motion capture studios or lab setting, it presents a significant challenge in more dynamic real-world applications. For example, in fields like healthcare or physical therapy, patients may vary widely in body proportion, and expecting exact bone length data upfront may not be feasible. Similarly, in sport analytics or fitness applications, users typically expect minimal setup. So the need to perform extra calibration steps or take manual measurements can act as a barrier to user adoption and limit the overall scalability of the system. Plus, this reliance introduces an overhead in terms of both time and resources. Calibration procedures often require specialization equipment or exact supervision, which may not be available in all deployment scenarios. So, this limitation could impact the practicality of mannequin in low resource settings or in application where the user population is highly diverse. So this addressing this limitation is an important area for future work. One potential direction could be the integration of learning-based methods to estimate bone lengths directly from the visual data, or the implementation of adaptive models that can tune themselves based on observed movement patterns. So finally, reducing or eliminating the dependency on pre-calibrated body dimensions would significantly enhance the usability, accessibility, and robustness of mannequin in broader real-world context.
So now I will be concluding the presentation. First of all, I would like to talk about key takeaways of this paper. So Manikin's core innovation is its hybrid design. Unlike traditional methods that rely on optimization or only neural networks, Manikin splits the problem. It uses neural networks to predict high level motion, where your shoulder or hip should be. Then for limbs, it switches to closed form math, predefined equations that calculate perfect elbow or knee angles instantly. This blend gives us both flexibility and precision. But again, speed and accuracy mean nothing if the poses look unnatural. Here is where Mannequin shines. It uses refined SMPL body model with hard limits on joint rotations, so no hyperextended elbows or twisted knees are observed. Then the neural swivel angle predictor ensures that limbs rotate naturally, like how your arm twists when reaching for a cup. So together these guarantees make mannequins outputs very similar from real human motion. Then the results of this model speak for themselves. On benchmarks, Mannequin outperforms both optimization based methods and pure learning methods. Optimization based methods are uh, accurate but they are slow, whereas pure learning methods are fast but glitchy. This model has shown itself uh, worthy in both of these categories. Again, the last point and very important point, this model provides a new paradigm for inverse kinematic problems with very much potential for real world application, especially when it shows good performance with respect to the old models like optimization based and pure learning based. It is very much useful for real time applications. So next I would like to talk about impact. Mannequin is not just a research novelty. It has shown a strong impact in many fields, like for example in VR/ARs. Imagine avatars that move exactly like you, of course without uncanny glitches. Also in robotics, robots that plan motions safely and efficiently can be made using this model. Similar types of impact is seen in animation, where studios could generate lifelike animations in seconds, not hours. Also, by setting a new standard for IK solvers, Mannequin opens doors we are just beginning to explore. Then I would like to talk about the future aspects. Now you might have a question of where do we go next from here? Well, there are two exciting directions. One is dynamic environments, which involves teaching Mannequin to handle objects, uneven terrain, or external forces. Then we have generalization, where we generalize this model to diverse body shapes or motions. Think of an athlete or patient or even non human characters. So, by this, I would like to conclude this paper and thank you.